Hey, good morning, afternoon, or evening, physics people. We're going to be looking at day 15 today in physics, once it opens up here. And we're going to be looking at drawing the pictures for the solenoid. And we're also going to be looking at, we're still talking about magnetic field, by the way, and we'll also be looking at the motor principle or magnetic force principle, where if you have a magnetic field and a wire that carries current in that magnetic field, you actually produce a force, okay, and it can rotate. That's where you can have some electric motor principle that happens, and we'll look at that in detail here as soon as our blackboard opens up. Okay, so this, this is day 15. Okay, we're almost to the end. We've got one more topic after this, and then our second hand in with gravitational and magnetic fields. I kind of threw that out to one. So this is day 15 of Unit 3. Okay, we're getting close to the end. And what we're going to look at today in day 15 of Unit 3 is we're going to look at the right-hand rule for a solenoid. Another word for a coil. Okay. We're going to look at factors that affect the strength of the field. And probably we'll look at those two things for sure. No math in there, just drawings mainly. And then we'll probably look at the force on a current carrying wire in a magnetic field, sometimes called the motor principle. Okay, and there is a formula for that one, but we might not get to that today. We'll see how far we get. There is a mathematical calculate formula for the size of the force that you can have. So let's start off right at the top here, the right-hand rule for a solenoid. So last day we did the right-hand rule for a current carrying wire, and we drew the picture. We drew a picture of the wire, and we also drew a picture of the wire coming out of the page and into the page as well to determine the magnetic field. So around a current carrying wire, we know that a magnetic field is created in concentric circles around that wire. And it depends if you're using conventional current. If you take your hand and grip the wire, pointing your thumb in the way or the direction of the conventional current, the curling of your fingers represents the direction of the magnetic field circles around that wire. Now that also applies for a solenoid as well, but a solenoid is a bunch of wire curled up in a coil, so then it makes it a little bit different. So let's take a look at the diagram for the right-hand rule of a solenoid first, and let's look at that by starting with the diagram. Now I'm going to draw two diagrams here. I'm going to draw the basic diagram of current coming into a coil and looping around, and the way that we're going to get the magnetic field. And then I'm going to draw a coil and pretend that we saw it in half and look at the cross section of it. So the first thing that we're going to do is those coil diagrams. So let's title that up. Magnetic field around the coil. So let's start off with a coil here. Get our marker out. So let's start off with making a coil like this. Okay, from left to right, it's going around the back, and then it's looping. That's back wire, then it's looping to the front. Back wire, looping to the front. Back wire, looping to the front. So we're going to put in here that the current is flowing like this. Okay, so we're putting in our current flow here. I might as well go right through all the coils here. So it's going in there, coming out here. So those little arrowheads in red represent the current direction. Okay, and if we take the right-hand rule for a solenoid, which I will put underneath my second diagram, so I'll just state it right now. If we take this and we go, okay, well, let's apply the right-hand rule of a solenoid. So that says a right-hand rule for a solenoid is grasp the coil with your right hand, curling your fingers in the direction of the current. Okay, so you're either grabbing like this or grabbing like this. Your thumb will point in the direction of the north magnetic pole. Okay, so that means if we're doing this one, it's curling around if we take it and pretend this is a coil here, okay, and it's curling around the back, and we grab it from the underneath, curl our finger around the back and then around the front. Our thumb is going to point that way, okay? So that's the North Pole. So if we're doing that with our diagram here, because it's going around the back, curling around the back, and then the front. So just under current diagram, just in case we're not clear on what the diagram means, the current is going around the back, and then over into the front. Okay, that's what we're getting. So that means that we're going to get the North Pole right here and the South Pole right here. And what the magnetic field looks like is it looks like a bar magnet kind of. So it looks like this. If we do magnetic field in green, we'll draw two up here. You can even draw a third if you want. I'm just going to draw two rungs of it. Okay, now we know that the direction of the magnetic field points towards the North Pole and into the south. So we can put all our green arrows. You'll notice there's lots of magnetic flux lines there. Oops, got that one backwards. So this is the magnetic field lines. Okay, you'll notice that inside the solenoid there is a large magnetic field. Okay, because they're close together here and they're more spaced out here. Okay, so if I were to draw the same diagram with the solenoid kind of sliced in half. Okay, so let's do, like if you were to cut the solenoid like this, these would be the loops of it. So I'm going to draw maybe 5 or 6 of these. Okay, so these represent the loops of a solenoid if we went and sawed it down the center. Okay, and these would be the wires cut in half as it loops around. And we'll say that for the magnetic field, which we did in red, we'll say that they're all coming out of the page on the top. On the top of the loop, it's coming towards us, the current direction. So there's dots in there. And on the bottom of the page, it's going into the loop. Okay, so top of the loop, it comes out, bottom of the loop, it goes in. Okay, so this is current in the loop, current going into the page, which we got on the top of the loop. And then this is current coming out of the page. Okay, and that's the bottom of the loop. So that means our fingers are wrapping around the top and the bottom. They're pointing into the page and then coming around the back. Okay, so that means the current is going from here up into there. Okay, that's the current direction. Now, if we do that, that means the North Pole is on the same side that we had it on the top diagram. And then we have our magnetic field again. Okay, that looks very similar. Okay, inside we've got we'll do a couple on the top. Oops. And a couple on the bottom. Note that they are very, this one I kind of jammed too close. So we'll just make it smaller. Okay, everything's pointing there. this is the magnetic field lines. Okay, so I'm going to ask that, of course, on a hand-in or exam to draw the magnetic field around a solenoid, current carrying wire. Okay, those are the two we looked at. Okay, so that gives us what it looks like around a solenoid. Okay, it still uses the same idea for a current carrying wire, but if you do a solenoid and you have a whole bunch in a loop kind of situation, you can come up with the solenoid loss. So what is the solenoid loss state? Well, let's just type it underneath here. Okay, stated it already, but for a solenoid, the right-hand rule for a solenoid, which means coil, wire, oops, did I spell that right? Solenoid. Grab the coil with your right hand. Okay, this is conventional current. Okay, control your fingers, curling your fingers in the direction of the current. Okay. Your thumb will point in towards the north pole of the magnetic field. Okay. So and then we can say three factors. Determine the strength of the magnetic field. Oops. Around the solenoid or coil, if you like. Okay. Okay, the first thing is the size of the current. The bigger the current, the bigger the magnetic field. Why worry about magnetic fields around high voltage wires that have high currents in them? Okay, it's pretty easy, directly proportional to how much current is going through. Okay, the other one is the number of loops that you make. Same thing. Okay, the more loops, the higher the magnetic field. More loops give a greater or give a larger magnetic field. And that both directly proportional. Okay, and the other one is the space between the loops in the solenoid. Okay, so this one is the only indirectly proportional one. Okay, the larger the distance, between the loops. And I think my head's probably in the way. I'm going to move this up. I don't have the preview on here, so let me do that. Just show the webcam here. Okay, sorry about that. I can't really see the screen. I can only see my preview there. So let's move this up. There we go. Okay, so the space between the loops, the larger the distance between the loops, the smaller the magnetic, or the weaker, we'll say, magnetic field created. And there we are, the three factors. And they're pretty commonsensical, especially if we know the kind of rules, common rules that we know, universal gravitation, how it works. We also know how electrostatics works. It's kind of the same idea. Okay, distance has the effect of lowering the force, and thus the magnetic field. Okay, so that was the solenoid and all the things about the solenoid. The only other thing I want to look at today is kind of like the motor principle, and that's a current-carrying wire in a magnetic field. So we're going to do another drawing. Now this one is three-dimensional, so I'll have to be careful on my drawing. And also I will kind of describe it as we're going so that we don't mess it up. And this is probably the last thing we're going to do today in this area. Okay, so this is the force on a current carrying wire. In a magnetic field. So if we have, we're going to draw the diagram first so that it's easier to see. So we should have probably done this on the other page. So I'm going to put this on the other page. All right, so let's draw it right at the top here. So let's use two magnets to represent the magnetic field. So I'm going to draw these in black, and I'm going to kind of do it in the middle here so that we can kind of have some space. Okay, don't start drawing yet. Let me kind of draw my idea. So we're going to have the south pole of a magnet here. You can go ahead and draw this part because this I can't screw up. And the north pole right here. Okay, so then we're going to have a wire in the magnetic field. Okay, so these are magnets. Don't need an I in there. I don't know. I was going to put magnetic. Magnets, and this is a current carrying wire. Okay, so here we have, that's the setup. Okay, so you can draw that thing. And we're going to have a current going down the wire. So the current is, we're going to put it in blue here. Let's use this arrow so that it's nice. Okay, so we're going to have current going down the wire here. We'll do it in blue. Okay. You can see the arrowhead there at the end. So this blue, this is going to be the direction of the current. Okay, this is going to be obviously conventional current again, not electron flow, but conventional current. So that's the direction of current. And then we're going to have a magnetic field created across here. So we'll do that in red maybe. Let's do it in a dashed line in red. Okay, so it's going to go north, south. So we have a magnetic field here coming across these two magnetic poles. So there's our magnetic field. Okay, and what we're going to call, because there's a formula for this one. So what we're going to call this red part is this is going to be, oh, I should have left the dotted lines on there. We need to go back to red here. Oh, come on, you. Okay, I need a red. So this is the magnetic field. Okay, and we're going to use the symbol B to represent its strength. For the current, we're going to use the symbol I to represent its strength. And we'll talk about those symbols in a minute. Okay, and now we're going to have to come up with a third color, because what happens, the right-hand rule states this. Okay, so this is a right-hand rule for, for a current carrying wire in a magnetic field. If you take your right hand, okay, so this one here, and you point your thumb in the direction of the current on the wire, okay, and basically point the fingertips of your hand, I guess, in the direction of the magnetic field. So thumb in the direction of the current, fingertips in the direction of the magnetic field. Your palm will open up in the direction of the force on the wire. So this is a three-dimensional law. Okay, so imagine this is a current carrying wire, okay, and imagine that the magnetic field is going, let's imagine that the current is going to the tip of the pen here, and that the magnetic field is going towards the camera there that way. So I would go like this, and that means point my thumb in the direction of the current, point my fingertips towards the camera, and that means magnetic field would push this wire up because my palm is opened up. Now, if it was the other way around and the magnetic field was still going towards the camera and the current was going this way, I'd have to put my hand like this, point my fingers towards the camera, point my thumb towards the tip of the pen or the current, and you notice my palm is facing down, so push it down like this, the wire down. So that's the that's the right-hand rule for a current-carrying wire in a magnetic field. Okay, and I'll write it out on the bottom here in a minute. Okay, so that means that if we look at our drawing on our page, put our right hand there, put our thumb down the blue line, point our fingers to the south pole, our palm is, so the magnetic field is coming up, is perpendicular to the current and the magnetic, sorry, not the magnetic, the force on the wire. So it's going to be coming straight up out of the page. So we'll use a arrow, and we'll go with this purple color, I guess. So like that, and it's perpendicular. So if we take our black pen here, make it small, we can say that it's perpendicular here and here. It's perpendicular to the field. So let's go with summarizing it with a little purple here. Let's get this, and then we'll put the purple on. Okay, so this is the magnetic, this is the force on the wire, not the magnetic, so we'll write that in the proper color here. Okay, and we'll note that it is perpendicular to both. I'll move this up because it's probably, my head's probably getting in the way here. Both the magnetic field and the current direction. Okay, so this is 3D diagram. Okay, so that this line, the force on the wire, we'll call F. Okay, and that's coming up out of the page, really, if you think of it. In our diagram there. Okay, so there it is. Okay, and we're going to relate the formula for a magnetic field with F, B, and I in a minute here, if we have time. Maybe it'll be next day, we'll see. But we do have to state the right-hand rule here so we know what it is. Okay. So the right-hand rule states, this will probably be the last thing we do because we're already at 34 minutes. And I don't want to go past 40. I usually like to keep it 35 minutes long or so. All right, so it states the right-hand rule for a current carrying wire in a magnetic field. Okay. Point your thumb in the direction of the current. This is of your right hand, of course. Okay. Point your fingertips of your hand in the direction of the magnetic field. Okay, when you do that, and your palm will open in the direction of the force on the wire. And that is the right-hand rule for a current carrying wire. Okay? Point your thumb in the direction of the current. Point your fingertips in the direction of the magnetic field. Okay, those are in the same plane of the hand. And then your palm represents the direction of the force. Okay? So, again, just to illustrate, if you have a pen, okay, and that pen tip is the direction of the current, and let's say going towards the camera is the magnetic field, we put our hand like this, point our thumb along the pen, point our fingers into the camera, and that tells us that the magnetic or the force on the wire is going to go up because of our palm. If it's the other way around, it goes this way. What if you were having the magnetic field coming out? You'd have to kind of take your right hand and go like this. It'd be either like this or towards you and get your force on the wire. Okay, there is a bit of a formula, so maybe here we've got a couple minutes. I'll throw the formula down for you, and then we will call it a day. So just to remind ourselves what I, F, and B are before we go is important as well. So let's do that underneath here, and let me space this up a little bit here. Okay, so just kind of bringing it up on my page here. Okay, so if we look at it quickly, we don't want to go too much longer. Okay, if we say that what is B and what is, okay, so B equals the magnetic field strength. Okay, and that's going to be measured in Teslas, named after Tesla. Okay, so unit after Teslas, and then F is going to be force on the wire. Okay, and that's going to be named in newtons. Okay, named after Newton. And I is going to be a current flowing in the wire. And that's in amperes, named after Ampere. Okay, so if you look at the formula, okay, it's basically F, and we'll do this a little more tomorrow, equals I times B sine theta L. And this is going to be the only one we don't know, it's the length of the wire. Okay, and this is the angle between these two. Okay, usually if it's 90 degrees, then it's going to be a 1 because sine 90 is 1. Okay, we'll work with that formula next day. We're going to stop at this point today, and that'll be as far as we go. We've got into about almost 40 minutes, which is a little longer than I should have went. See you tomorrow.